Okay, it's October 27th, Monday morning, and this is lecture 12 of our DTCO course 2025. I will start my lecture um, on time at 9 o'clock, and I'm just sharing the information about this delayed postponed lecture. Lecture 12 was actually scheduled to be October 20th, 1 week ago. However, in order to prepare some additional material for selective epitaxial growth, I postponed my lectures by 1 week. Quite fortunately, in this week, we have 1 week of break due to midterm examination in GIST, but we don't have any midterm examination in this course, so I'm utilizing this opportunity to catch up the lecture progress. Okay, so lecture 12 will be made today, and lecture 13. So next one will be on October, of course, 29th, Wednesday. So then after that, lecture 14 will start as usual next Monday. Okay, so although I cannot check the attendance, uh, but I will not check the attendance. So because this is not the offline um, on-site lecture, but it is an online lecture. So I will just do uh, the usual YouTube live streaming. And if you are not in the right time, then just to watch the video later. Okay, so it's 9 o'clock and let's start our lecture 12. Thank you for your patience. Mm, and lecture 12. In this lecture, I will show you uh, result a result of my kinetic Bayes Monte Carlo simulation. So let me just introduce what is uh, meaning of this kinetic lattice Monte Carlo. So here we have the word corresponding to the Monte Carlo. Monte Carlo method is a stochastic method for simulating discrete events over time. So we have a certain governing equation, and in many cases we just solve using some numerical schemes like a discretization. The entire system is discretized as a set of algebraic equations, and we just integrate it over time. However, in this Monte Carlo method, instead of solving the entire system, but we just consider an instance of a certain trajectory. So if we have a certain random numbers, then we just coin it, and using that generated random number, we just mimic the progress of our system. And if we wait for a long time, or we just repeat it again and again, then we expect that our result will be quite close to one observed in real system. So that is Monte Carlo. So Monte Carlo is quite powerful, and of course it takes some time to mimic the real system, and of course we have to think about the statistical variation. But in this case, in this selective epitaxial growth, actually Monte Carlo method is quite suitable. And we can find another specification here. lattice, and here lattice. Uh, there are other methods like or there are like a kinetic Monte Carlo. Kinetic lattice Monte Carlo is a subcategory of kinetic uh, lattice Monte Carlo. And here the term lattice means that we assume a predefined atomic site in a crystalline structure. So we do not consider an atom located, for example, here. In this position, in our simulation, atoms cannot occupy this position. It occupies, for example, this atomic site or not, and this atomic site or not. So positions are already predetermined, so we can just consider whether it is occupied or not, occupied or not. This kind of assumption can drastically simplify our system quite a lot. So we can just determine whether that is now occupied or unoccupied. So this lattice term greatly simplified. If we consider general kinetic Monte Carlo, then actually we must consider the motion of motion of atoms, silicon atoms, hanging around this position, but we do not uh, consider this kind of degree of freedom. And implementation, a prototype of this kinetic lattice Monte Carlo simulation has been implemented in Armstrong craft during the 1 week break. But this is quite much experimental implementation, so it will not shared with our students. So I will just show my result and come back to voxel based usual mode of Armstrong craft. So please understand this limitation. Uh, so this is one shows the atomic structure of a crystalline silicon, and this is a cubic a cube, and here we have 0.543 nanometer. So if we consider our usual size of voxel considered in our um, Armstrong craft, then typical size was 1 nanometer. So this is corresponding to twice larger along each direction. In our voxel-based consideration, we say that this large blue box is corresponding to one variable. Is there existing this voxel or not? However, right now we consider so many atoms inside this box, this blue box. So of course, kinetic lattice Monte Carlo simulation right now provides us much detailed information about its structure. But of course, that is obtained with the cost price of spending more storage in computer simulation. Okay, so anyway, let's quickly go to our atomic structure. So in previous slide, we have seen this atomic structure of a crystalline silicon. In this case, if this is the G direction, then that is corresponding to 001 direction. And here we have X and Y, and our channel is also aligned this direction. So this is corresponding to our 110 direction. And our usual configuration, also another axis is corresponding to this one. Actually, it is laid on this XY plane, so I have to draw in that way. And that is corresponding to -1, typically called as 1 bar, and 1, 0. This is the direction of our constellation. So since we are typically working with 0, 0, 1 vapor surface, actually when we make a top view, that is corresponding to this view. So let me just place our atoms in. So now, as you can see, this is corresponding to 110 and 1 bar 10, and this is corresponding to 110 and 1 bar 10. Now we are looking this system from the top. So then how does it look like? And this is the arrangement of our silicon atoms. And here we have certain numbers 0, 1, 2, 3. Although when we make a projection of our atoms, all of them are placed in this lattice point, so integer multiples of certain uh, unit distance, and also same one here and there. Actually, uh, this distance is corresponding to square root 2 of 2 divided by 2 times a. So a equal to 0.543 nanometer. And yes, now we have this quite regular distribution. But when you make a prediction, but different numbers in these two or these four cases means that their g coordinates are different. Although when we make a projection, they are placed in this way, but this one is deeper and this one is more close to our eyes, and this is even more closer, and it is even further closer. After that, then now the number 4 comes in, and number 5, number 6, number 7. So every 4 atoms or every 4 layers, they are returning to the original position. This is the assumed coordinate system. We assume 001 vapor surface and 110 channel direction. And in this case, we can find 4 layers, and with these 4 layers as a unit, every time it is repeated. So in this case, using a triplet IJK, then we can uniquely specify a position of an atom. For example, this ij, a pair of two integer numbers that is used to specify uh, this group of 4 atoms, and k corresponding to the 1 to 0, 1, 2, 3 that specify the position. So for example, let's say that this is corresponding to, let's assume that this is 0, 0, and we say 1, 2, 3, and this is 1. So 3, 1, 0, that is corresponding to this setup. And 1, yes, this one, 2, this one, and 3, yes, this one. And when we say instead of that, so 4, 1, and 3, then that is corresponding to this one. So actually this is not that important for your understanding on selective epitaxial growth, but well, in my implementation, I have assumed this kind of indexing system. So now you can see that in our system, we have quite a regular what we do is just to check whether this one is occupied or unoccupied. And this one, that information is enough to build up our entire system. Okay, so now let's go to the visualization. Let's assume that we have a certain uh, system having 9 times 2 array in atoms. So 1, 2, 3, 4, 5, 6, 7, 8. So here is a 1, 2, 3, 4, 5, 6, 7, 8, and one more. And here we have 2. So this is quite similar, the size of this hand-drawn um, diagram. And when we visualize it in the parabolic program, then now you can see it here. Well, this one is corresponding to one atom. So why it is not that much smooth? Why it has a certain polygons in its surface? Yes, this is just due to the visualization setting, so you can make it more beautiful. However, I think that this is enough for our understanding. So this is the top view. So now you can understand, well, now you can understand, although here, for example, here and here, and also here and here, we have 4 atoms. Yes, and they are occupying the integer multiples of x directional distance and y directional distance. But in this three-dimensional view, this one seems to be the closest to us, to our eyes, and this one is, yes, a little bit deeper and deeper and deeper. Of course, if we go to the next level of deposition, or not actually deposition, epitaxial growth, then our silicon atom will occupy this position. After that, if we go to the another layer, then it will occupy this position. Yes, so this is quite straightforward. Then which one is preferred? So why do we have a different preference for different atomic size? So this is related with the number of nearest neighbors. So in this work, I will just consider first, second, third nearest neighbors. So let's say that this is the reference atom we wanted to consider, and please try to find out the first nearest neighbors. Then you can find it here, and also not shown here, but you can find also here. And are other ones are found also here and there. There are 4 first nearest neighbors, and their distance is corresponding to this number. Beyond this first one, it becomes a little bit more complicated, but according to just a careful examination, we can find that there are 12 second nearest neighbors, and also there are 12 third nearest neighbors, and their relative position can be easily obtained if we have I, J, K. Then there are certain rules to find out the first nearest neighbor, second nearest neighbor, and third nearest neighbor. So finding the position, atomic position of this nearest neighbor, that is not that difficult. So it's a uh, relatively easy, relatively easier than we might expect. Okay. So now we can quickly count the number of first nearest occupied first nearest neighbor site and also occupied second nearest point and third nearest points. So that is not that difficult. So now let's just think about this one. If we consider 20 by 10 nanometer rectangle in its XY plane, then this is the atomic configuration seen from our top surface. This is a vertical direction z and x, y, and again y is corresponding to 1 bar, 1, 0, and x is corresponding to 1, 1, 0. And although this is 20 by 10, you can find that in reality here we have a 52 by 26 array of atoms in this plane. It is because the distance between these two atoms is much shorter than 1 nanometer. That's the reason why we have more points than we expect. So in our previous implementation based on voxels, then this 20 by 10 will give us just 20 and 10 boxes here in this plane, but we have much more atoms in it. And anyway, we will use this configuration. Then if we grow something, so silicon, for example, then what will happen? There are so many candidates for epitaxial growth. So, for example, this one is the top surface, top layer, and this one is corresponding to top layer, and this one is top layer, and top layer, and top layer. There are so many top layers, and the next part will be next position, next allowed position for our added atom will be this one or that one. There are so many candidates for occupying. So we must randomly select one point. After selecting one point, then now we will have a certain atom here. Then local atomic configuration is changed. So number of nearest atoms are also changed. Also, we must recalculate the relative probability to add one more atom, so that affects, naturally affect the resultant shape of our epitaxial growth. Okay, so in this case, I just follow the work by Lenu Chen, my former colleague in Samsung, and he's now in the startup company. So following Lenu Chen et al., the adsorption rate. So here adsorption rate means that the corresponding to the probability where one atom is placed at that position. That is simply calculated by this rule. So here we have binding energy, and if this binding energy is higher, then we have a higher probability to add one atom at that point. So if everyone every position has the equal probability, then that is just a uniform distribution. However, once one atom is added, and now this atom is being used as an additional nearest neighbor, for example, this guy. if we consider this position and that position, yes, this one has a much higher probability to be uh, occupied in the next step because this one doesn't have just additional neighbor. However, for this guy, this one can be regarded as an additional second nearest neighbor. Good. So this second nearest neighbor greatly improve the probability of selecting this position. So this total binding energy is obtained from the number of our first nearest neighbor and number of second nearest neighbor and third nearest neighbor. Of course, if we become more rigorous, then of course we can think about additional 3D expansion, but we don't consider this one, just to cut off at third nearest neighbor, and his parameters are corresponding to this one. This parameter is 0.15 eV, and this one is corresponding to 0.12 eV. Yes, there is a little difference between second and third one, and of course, the first one plays the most significant role. Yes, and we have this kind of expression. Why do we have this kind of expression? Actually, I'm not an expert on this kinetic lattice Monte Carlo, so I have a little idea about why this total binding energy is obtained by in this way, why we consider linear contribution for this one, and why we consider non-linear contribution from the first nearest neighbor. I don't know. But if we accept this kind of a total binding energy, then the lesson is quite simple. If we have more nearest neighbors and there is a much higher probability to occupy that site in near future. So now let's think about this one. If we have a clean 001 surface as shown here, as shown in this clean surface, then every candidate points have the first nearest neighbor of 2 and second 4 and third 6. However, when a certain position is selected and after that the one corresponding to this one that has changes in their nearest neighbor. So please have a look at this one. Yes, first one doesn't change and third one doesn't change. Only changing occurs is N2 second nearest neighbor and just to one additional second nearest neighbor is found. However, only one atom difference, but at 600 degrees Celsius. This is known to be a typical fabrication process temperature, and this additional uh, second nearest neighbor contribute additional 0.15 eV, and this additional 0.15 eV is more than 7 times higher absorption length. So that is huge. So that's the reason why when we just repeat this kind of adding more atoms on this surface, uh, atomic positions, atomic sites occupied ones are not randomly distributed. So once one is landed over a certain point. After that, it is clustered, and you can find some certain island. So let me just show you the result of that consideration. Let's just add some atoms. So how many atoms? So we just add 676. This number is corresponding to 52 times 26. It means that the number of the first candidate atomic site. So if it is really uniformly distributed, then using this number of atoms, this surface can be just uniformly covered by one layer. But when you have a look at this result, then you can find these points. Here, we don't have any additional atom. And instead, you can find that here we have a certain island of atoms, and also you can find certain island of atoms. Oh, by the way, I have made an assumption of a period boundary condition. Uh, Here and there they are connected. Here and there they are connected. So there is no boundary effect. It is assuming infinitely wide um, surface here. Well, now you can understand the main mechanism to make the difference between just a random selection is the absorption rate, and that is related with the number of nearest neighbors. So if we have a certain point already occupying certain uh, atomic site, then it is growing faster than the unoccupied site. Okay, so now let's go to this so-called hardware. So this is not a universally accepted word, but anyway, we introduce hardware. These words do not provide nearest neighbors, so it reduces the number of nearest neighbors. For example, let's come back to our clean surface example. Yes, N1 was 2, and N2 was 4, and N3 was 6 in a clean 001 surface. However, when a hard wall exists, it means that I have assumed this one. Here we have a wall. However, instead of assuming this periodic boundary condition, so it can see something here, but instead of that, we assume that this is just this one is hard wall, and also say that, for example, here we have hard wall. So then this one previously had some neighbors found in here. Now there is no contribution from this hard wall. In this case, the number of nearest neighbor is reduced quite significantly. That is corresponding to the probability of adding more atoms. Of course, since the structure uh, is different layer by layer, so depending on its layer k number, the vertical position, we can have many different configurations. But anyway, um, the reduction of total binding energy is quite significant. Although there is a layer with no reduction, but other ones it is corresponding to 0.6 EV reduction. So it is corresponding to almost no probability to have additional atom growth in this point. So simply speaking, if we have a hardware, it reduces the number of nearest labels quite a lot. So there is no sufficient anchors to keep our additional atoms secure. So that's the reason why nearby this hardware there is almost no architectural growth. The hardware significantly slow down the growth. So now let's have a look at the impact of this hardware. So in order to show you that information, I have introduced quite a long 50 nanometer long structure. Oh, then we have to consider so many uh, atoms in it. So instead of considering this 50 nanometer long system quite huge, but instead of that along this y direction, we just made very short distance, and at the same time we impose periodic periodic boundary condition along this y direction. So it means that we assume just a wide structure along this y direction. This y directional it is just uniform, and we consider only confinement, geometrical confinement along x direction. The channel direction we have a confinement. It can reduce the computational burden significantly. But, well, it is quite good for our educational purpose, not realistic for our actual application, but I think this is enough for our purpose. So along the y direction, only 3 units are assigned, and we have used the periodic boundary condition. And at the initial point, we had only this red colored silicon substrate. After that, I tried to add 28 layers corresponding to 3.8 nanometer of these green ones. So they are also silicon atoms, but in order to uh, show you the growth clearly, I intentionally introduced different colors, but they are all silicons. And if we do it without hardware, then we have almost uniform profile. Well, you can find that there is a little bit less growth and more growth here, but compared with the average thickness corresponding to about 3.8 nanometer, up and down is not that much. So if we go more and more, then this non-uniformity can be insignificant. So that's the reason why that's the way we assume the uniform growth. Although everything in reality is a probability, so we must have a certain kind of this higher position and lower position and rough corresponding to roughness, but that roughness is not that significant in this stand. And now let's introduce hardwares, and I will use blue color to represent this one. These blue colors are not counted as the nearest neighbors, although they are occupying certain position, but when we count the number of nearest neighbors, I will not count them, then what will happen? So let's have a look at this one. 12 layers and 20 and 28 layers, and 28 layers is corresponding to this slide. Yes, without boundary, we had a more or less a uniform profile, but when you have a look at 28 with this hard wall, yes, and hard wall, then now you can see that this is the profile after the same amount of atoms are added. So why do we have this drastic change in our grown profile? It is because here and there the growth of our silicon, that is almost prohibited. Yes, so using this one, starting from this almost stop position, now we have certain typical, quite typical slot, and we have also quite typical slot here, and also we have another one. You know, this one is corresponding to, of course, the direction or surface corresponding to 0, 0, 1 surface. But here we have also other one that is corresponding to 3, 1, 1 surface, and this is most steeper one that is corresponding to 1, 1, 1 direction. So now you can understand this typical shape of our epitaxial growth is determined by this existence of hardware. Internally, in this system, even without this boundary condition, it has certain preference for 0, 0, 1 surface. However, without boundary condition, it does not show. But when we have these boundary conditions, which prevent the free growth of our epitaxial layer, then starting from this point, now we have we can see the difference of directional growth rate. So that is shown here. So let me just give you another example. I think that this is the last example of our lecture today. And here we have another example of a 20 nanometer thick film. Also that is shown Lenny Chen's paper. Here we have in total 60 nanometer long scale. Here we have 60 nanometer. Then this is blue hardware. This is a 20, and this is 20. And also we have certain another 20 nanometer wide trench. So this red one is corresponding to silicon, and initially we have just hardware and hardware. And when we start our selective growth, starting from this bottom position, additional silicon atoms are added. So you can easily understand this is quite much corresponding to this system. So although the size is different, previously it was 50 nanometer long, and this is just 20 nanometer long. After that, I just introduce some electrons corresponding to 147 layers. If it is uniformly distributed, and I made an intention to cover just top of our hardware if that is uniformly distributed. However, when you have a look at this result, then of course, due to this boundary condition, the growth in this wall side is much slower than the growth in this central point. And you can see that there is also quite a steep position here, and this is corresponding to 311 surface. Of course, in the nearby center, here we have lower ones like 311 surface corresponding to more close to 100 surface. So later it will become more sharper because growth rate for this 311 is faster than this 111. So eventually the system will be dominated by only 111 surface. So simply speaking, even when we have just a 20 nanometer deep trench, but still already we have the dominance of a 111 surface. So what will happen if we add additional atoms? Then this is the result. I have introduced twice atoms, 147 and now 294 layers. And when you have a look at this one, now this original trench is fully filled with this newly added atoms, and now you can see that here we have a quite clear shape of our 111 surfaces. So of course, why it has a certain irregularity here? Because we have already done the Monte Carlo method. So if I learn the same code with different time scale or different time instance, if I learn this code today, then I will have a different result. But more or less, they will share the same uh, features like existence of dominant 111 surfaces. So now you can see that the diamond like shape can be obtained from this kind of a system. So simply speaking, I wanted to say that from today's kinetic lattice Monte Carlo simulation result, now it is clear that in our silicon crystal system, intrinsically we have differences in the directional growth. So 100 that is faster, and 111 that has a slower growth rate. But combined with this boundary condition, now this difference is realized, and we can see this clear diamond like shape. Okay, so okay, thank you. And up to now we have shown this kind of result for our simple structure. However, please think about our original aim. We are currently trying to mimic the entire process flow. Um, so this one has just 60 nanometer, and along this direction, its size is just well about about slightly longer than 1 nanometer. not shorter than 2 nanometer. So if we consider the size of our realistic system, keeping this kind of description, kinetic Monte Carlo, that is not feasible at all. So we must anyhow transfer this lesson to our voxel-based simulation method. So that will be covered in our next lecture, lecture 13. Okay, today we don't have any kind of attendance check and homework, so just to watch that video, and on Wednesday I will just start our usual lecture style, giving you some homeworks and yes, but in that even in that case, I will not check your attendance. Okay, thank you for your attention. And if you have any question, then please send me an email or come to me before our lecture start. Okay, thank you and see you later. Bye.